Okay, good morning, everyone. We'll continue with lecture 24. And last time we were discussing standard normal. Turn off your microphone and turn on your microphone when you have any questions or doubts. Attend tutorials to practice more problems. And chat sometimes is not reliable, so I may not be able to look at your question. I try to look at your questions, but sometimes it hangs. So, okay. This is the topic for today, today's class. We will continue with continuous distributions, and we were doing standard normal, and we will continue to do a little bit of that, and then we will go to normal distribution. So there is standard normal with mean 0 and variance 1. So that's the standard normal, and then normal could have like some general mean and variance. It will still look like a bell curve, but with different mean. Okay, not necessarily 0, but it's like symmetrical about the point, not necessarily about origin. And the variance also may change. So that will be the normal distribution. Then we will see gamma distribution. Okay. So gamma distribution is related to like exponential distribution. So we will see that how. So properties of the gamma distribution, and we'll see some solved problems. So, and then if we have time, then we will look at mixed random variables. So mixed are like neither fully continuous nor fully discrete. So we can have such cases as well. Okay, so let us start with the standard normal. And last time, if you recall, we were deriving the bound of the phi function, right? So if z is normal 0, 1, then we recall that the CDF, which is phi of x, is nothing but probability that z less than equal to x. So that's the phi x is just a notation here used for CDF of normal. Then for all x greater than equal to 0, the phi function satisfies the following bound. Okay, so this is the bound that it satisfies, and these bounds are useful. We will see. Okay, in future. So last class, if you recall, we proved the upper bound. Okay, so upper bound is something we did. Now today we will try to establish the lower bound. Okay, so upper bound was done. Now let us focus on the lower bound. So to prove the lower bound, we will take a. So let us say we define some function hx. Okay, so here I will show the lower bound. So to show lower bound, so to show lower bound, let us define some function hx. Okay, so hx is defined as qx minus 1 by square root of 2 pi and x by x square plus 1 e to the minus x square by 2. Okay, and yeah, this is for all x greater than equal to 0. So if you can see, what I have done here is like I have done qx minus this lower bound, right? So what I have done is like here. So what I have done is I've done this. I've taken this qx and then minus 1 over square root of pi 1 by square root of 2 pi x by x square plus 1 e to the minus x square by 2. And then what I have to show is like this is, and what is qx I have not defined, right? So qx is 1 minus phi x. Okay, so there are too many notations here. Okay, I'm not writing it down, but so qx I will take it as, let's see, what would be the good one? Qx will be, so what I want to prove is that qx minus the lower bound is greater than equal to 0. So yeah, so qx will be 1 minus phi x. That's my intention. Okay, so qx is 1 minus phi x. Okay, this is phi. Okay, So what I have done here is that I have moved this here, and this guy is like qx. I used now another notation for 1 minus 5x. Okay, so qx will be the probability that z is greater than x, right? So because this is 1 minus of that, and I have so in other words, what I am trying to say is that qx minus the lower bound is greater than or equal to 0 if I can prove. Okay, so what I have defined is qx minus the lower bound. Okay, and if I can prove that this is like greater than or equal to 0, and this is anyway defined for all x greater than or equal to 0, right? The bound. So that would suffice. Okay. So now the question is this hx as a function of x greater than or equal to 0? That's where our focus is now. Okay. So this is the hx. So can we prove that this is like greater than or equal to 0? Okay. So so we need to look at the properties of hx. Okay. So properties of hx. So if we look at the properties of hx, what do we have? Let us calculate h of 0, right? So h of 0 is how much, right? So it's like we have to put 0 here, right? So it's like q of how much? Q of 0, and then here it will be how much? 1 by 1. So this is like, yeah. So it's 0, right? So it will be 1 here, and this will be 0. So it will be like 1, right? And so q of 0 will be how much, right? So let us write down first and then see. So q of 0 minus, and this guy will be basically 0 because x is 0. Okay, so this is 0. So this is nothing but q of 0. Now q of 0 is q of 0 is phi of 0. Now what was phi of 0? Can you tell me in the chat what was phi of 0 from the last class? Phi of 0, anyone recalls phi of 0? Half. Yes, thanks, Anmol. It's phi of 0 is half. Okay, good. You're following then everything. So it's 1 minus half, right? So 1 minus half, so it's half. Okay, so that is done, right? Look, what is my plan here, right? So I'm trying to prove that the function. Look, our goal is to prove that hx is greater than or equal to 0, right? So that will prove the lower bound, right? Now, for a function to be greater than or equal to 0, somehow like we have to show, yeah, I mean, you have to prove that it's greater than or equal to 0, but what are the tools that you can use from, let us say, from calculus, right? So what you found so far is like h of 0 is half. Okay, so it's like at the, if you draw the axis, then at 0, you have proved that h of 0, which is here, is, let us say, half. Okay, and then we have to prove that somehow this hx function remains above. Okay, so one, I mean, what are the ideas from calculus you can try to invoke here, right? Like, look, one possibility is what? One possibility is that it's half here, and obviously to prove that it's like above this, right? So you have to prove that things like this never happens, right? So it's like never negative. That's what we are trying to say for all x greater than 0, right? So one possibility is that you prove that although so at the boundary point 0 you got half, and one possibility is to prove that it's like always increasing function. Okay, so this is like very safe case. Okay, so it's very safe that hx is always increasing if you can prove that hx is always a increasing function. Now, what is the property of calculus that proves that a function is always increasing, right? So it's like the derivative has to be positive, right? So that's something we know from calculus. So the derivative is positive. This means that the function will always increase. So at 0, it's half, and after that, it's always increasing. So it is always greater than equal to 0. Okay, that is one way to prove, right? But it may happen that it's not the case. What if the function is actually decreasing? Now the question is like, what are the ways like it can go down, right? And if it is decreasing, then what we really are worried about is what is the asymptotic nature of the hx, right? So what will happen as x tends to infinity, right? So here like so here like we have a few cases to look at, right? Because hx is going to infinity. So one possibility is that hx at some point, like hx tending to infinity, and it comes below. Okay, so that will violate that this is not greater than equal to 0, right? So one possibility is that as x tends to infinity, hx goes below this x-axis. So that will violate, and then we cannot prove the lower bound, right? Another possibility is that it may happen that as x tends to infinity, hx is actually positive. Okay, so the asymptotic nature is that in infinity it remains above. Okay, so one possibility is that hx as x tends to infinity, let us say we prove that it is like greater than equal to 0, but there is a chance that in the middle it may go down like this. Asymptotically it may like again like remain positive as x tends, in the limit x tends to infinity it may remain above, right? But then these are the cases where again our lower bound will be violated. So so these are the possible scenarios we have, right? So one possibility is like, let us say hx tending to infinity is guaranteed to be positive. Okay, and then to avoid these cases where it may go down, right? The thing is like this guy is above 0, right? So here it's fine. And asymptotically, let us say it became above 0, right? So something like that, it's above 0. Okay. So to discard these cases, what do I need here? Like, so in terms of slope, what do I need, right? Because if it has to become greater than 0 asymptotically, it has to come up, right? So this graph has to come up. In other words, at some point, its derivative is going to be positive. Okay, so in these cases, its derivative has to be positive for some x, for some x. Like since this is continuous for like many x, it has to be positive so that it can go up again, right? So this is like so this condition will happen when yeah, at some stage it's going up. Okay, so one criteria is in this case would be to violate these cases, right? So in other words, it has never been the case that it went down and then it came up. Okay, so that's one case where we will prove that hx has always remained positive. So if we can prove that like this is never holds, right? So never holds. Okay, so this is one. So we may be in the two cases. The easiest case is that at the boundary it's half, it's always increasing. Done. Okay, nothing. But the other cases are like, okay, it is going down, but what is the guarantee that it still remains up? And asymptotically, I know that it does remain up. Okay, so then we need to rule out the case where hx decreases and then increases. Okay, because it has to increase because asymptotically it has to come up, right? So then we have to discard these cases where hx is like greater than 0, greater than equal to 0, right? In other words, if we can prove that h prime x is less than 0 for all x greater than equal to 0, and hx is let us say even if it's like equal to 0, okay, as x tends to infinity. Okay, so this is like always less than 0, and even though h is approaching 0, it doesn't matter. What matters is less than 0, right? So that's not happening. So this will prove us that hx will behave something like this. Okay, and asymptotically only it's going to 0, but it is never going down. Okay, because in the limit it's 0. If it especially if like the slope is always negative. Okay, so it's never going down, because if it went down then it has to come up. If it has to come up, then slope is going to be greater than equal to 0. So that will that will like that will like violate. If we have proved this, then that will violate this criteria, right? So these are the plans we have in mind. So let us see if we have something to show this, right? So let me clear these things up and try to prove this. So we will be in the second case. Okay, so like what I described is the second case. We will not be able to prove that h prime x is greater than 0. So that was the easiest case. We would rather have the second case. So we have h0, which is the first property, and the second property is that limit as x tends to infinity, h of x. Okay, so x tends to infinity, what will happen to this guy, right? So this is limit x tends to infinity. So let us minus, so limit distributes, right? So x tends to infinity, 1 by square root of 2 pi x by x square plus 1 e to the power minus x square by 2, right? Okay, so what happens to this guy, right, as x tends to infinity? So this guy, can you tell me in the chat what will happen to this term as x tends to infinity? 0, okay. So it will be 0, right? Like this guy is going to 0 anyway, right? So this guy is going to 0 because this is this. So this guy is going to 0. There is no issue here, and this guy starts dominating, right? So this guy starts dominating over this guy. Okay. So the denominator will become unusually large, and like even if you don't go by that, this is still a lot more powerful, okay, than this expression. Okay. So there are like there are results like this, right? 2 to the x or x to the 2, like which is larger as x tends to infinity, right? So these are the results, like you may recall, right? So but in this is a simpler case here. This guy will start dominating over this because this will grow much more. So this is also going to 0. Okay, individually they are going to 0. And okay, so this is going to 0. So everything, the focus is here on x tends to infinity. So what do you think? X tends to infinity qx. Okay. Yeah, so the previous answer was by Utkarsh and Mehul got correct. Okay. Now tell me the other answer. Qx as limit x tends to infinity. Which property was this? Do you recall the property number? Like we wrote down a couple of properties, right? 1, 2, 3, something like that. Anyway, like no need to memorize those property, but we know the number of those property, right? But we know that this guy is like going to 0 because this is the property that we proved. Okay, this property we proved it, and you can prove it again from basic principle. Okay, it doesn't matter. So this guy is actually 0. Okay, so you see we are building up for the next case. So what we have right now is that at boundary it's half. Asymptotically at infinity, let us say this is like, I mean, it's absurd to say that some place is infinity, but let us say somewhere we have infinity and hx is 0 here, right? So now the only thing that is left for us is to guarantee that h will never do something like this. Okay, because those will be the places where hx is going to be 0. I mean below 0, negative, right? And to guarantee that, if we can prove that the slope of the hx is never going to be positive, so this will violate, this will prevent these cases to be had cases, right? So next thing we need is we need h prime x, the slope, to be always negative. Okay, you see, so it's always negative. It's never goes down and then up. Okay, so only these cases it will. So if we could prove that it is negative, right? So we have to do the derivative now of h prime x. So let us do it here. So hx is I will write down copy the hx here. So it's qx minus 1 by square root of 2 pi x by x square plus 1 e to the minus x square by 2. and for all x greater than equal to 0. So this is hx, and we do the derivative of this with respect to x, right? Okay, so if we do the derivative of this, what do we get? So what do we get as a derivative of this, right? So if we do the derivative of this, I claim the following, and I'm skipping a few steps for the derivative here. I would trust you that you will find this expression. Okay, so what I claim is this. So I leave this as a homework for you to compute this derivative. What I will be left with after the derivative is minus x square by 2 by x square plus 1. Okay, so after taking the derivative of this with respect to x, after simplification, this is what I claim to get. Okay, so this is like check that this is the derivative of this. Okay, so there are a couple of steps needed here. I'm skipping those. So this is like for all x greater than equal to 0. Now this guy is surely negative because this is positive. Okay, this guy is positive. Okay, so this is like strictly positive. Okay, so this is also strictly. So this guy is strictly negative. Okay, so this is like less than 0 for all x greater than equal to 0. Okay, so from here, what I have shown is like this is h prime x. Okay, so this is the h prime x, which is negative for all x greater than equal to 0. Okay, this is what I've shown. So what we note is that h is strictly decreasing. H is strictly decreasing. That starts at h0 is half. Okay, so it's important that it starts from the positive value, right? And it decreases as x increases, right? And it decreases as x increases, and it approaches 0 as x tends to infinity. Okay, so this implies that hx must be greater than equal to 0 for all x greater than equal to 0. Okay, so this is how we prove this lower bound, right? So if hx is greater than equal to 0, then this means that this qx is like greater than equal to this, and qx was nothing but 1 minus phi x. Okay, so this proves the result. Okay, so we can stop here. I've left this in the interest of time to do this. This should be simple. Okay, so you put qx is 1 minus phi x, and then phi x expression is known to you, so you can do these derivatives. Okay. Okay, so what we have done is standard normal distribution, and now I will do something called normal distribution, just normal. It's not really standard. Okay, so you can think of it as a non-standard. Okay, so a general normal distribution, how it will look like. Okay, so we have seen standard normal, and any normal random variable can be given by this, by shifting and scaling. Okay, so z is the standard normal. So this is like 0, 1, and you can obtain any other normal, not necessarily standard, by doing this kind of a linear transformation. Okay, so this is a linear transformation. So it's multiplying by a scalar and then translating by another scalar. So sigma and mu are scalar here. Sigma is greater than 0 here. So by doing that, you obtain a normal distribution. Okay, so x will become a normal distribution now with mean, mu, and variance sigma. Okay, so let us calculate that, what I have said. So what is the mean of x? Okay, so this is the expectation of x. So mean is the expectation of x. So apply the linearity. So expectation of x is the sigma will come out due to linearity of the expectation, and then we have this. Okay, but expectation of z is 0 because z is since z is standard normal, so that becomes 0, and then you are left with mu, and then variance of x will be again you apply the variance property, like variance of ax plus b is nothing but a square variance of x. So that's the property that we have we have proved for the variance. So that's what we are going to apply. So this will be sigma square variance of z. Now variance of z is 1. Okay, so this will be just sigma square. Okay. So in this case, for a normal distribution, we write it like this. Now in place of 0 we have mu, and in place of variance we have sigma square. So this is called normal distribution. And conversely, if x is a normal distribution, then you can create a standard normal by doing this kind of a transformation. Okay, so if someone gives you a normal, then you can translate this into standard normal by doing this proper scaling and then and shifting and so on. Okay, so you can prove this, that after doing this, the expectation of z, okay, using the linearity of expectation and so on, you can prove that the expectation of z will become 0 and the variance of z will be 1 now. Okay, so this I leave this as an exercise. Okay, so this like check this. Okay, I'll put all this in the assignment. Whatever is missing here, I will put this in the assignment. Okay, so this is a check we can do. Okay, so what we observe is that from standard we can obtain a general normal distribution by doing this linear transformation, and then this scaling factor becomes the variance, and then this shifting parameter becomes the expectation. And conversely also, if someone gives me normal, then I can get standard normal by doing this type of transformation. Okay, so now let us calculate the CDF and PDF of the normal. We have seen CDF and PDF of the standard normal, but now let us do CDF and PDF of the normal. So to find the CDF of normal, we have the following. So let us calculate, right? So this is the notation for the CDF. And this is by definition, its probability that x is less than equal to x. Okay, so this is equal to, now in place of x, I can write like this. So if x is like a normal, then it can be seen like this, right? So I can write this using standard normal by shifting it by a mu and by scaling it by the variance. So x is equal to sigma z plus mu is less than equal to x. Okay, and so this is the same thing. So I can move mu on the right side, and then I can divide by 0 without changing the, divide by sigma without changing the inequality, because sigma is positive. Okay, so this inequality should be okay for you. Okay, so mu can be positive, negative, doesn't matter. I can move the mu on the right side without changing the inequality, and while dividing you have to be careful not to change the inequality. We have to divide by the positive, and sigma indeed was positive. That's how we have, right? So that's why we already assumed there. Okay, so sigma is positive, and this by the that we have introduced is nothing but phi. Okay, so phi is the CDF actually. Okay, so phi of x minus mu by sigma. Okay, now so yeah, we leave it at 5. Okay, as I said, 5 values are tabulated. Okay, so you don't have to really do those complicated integrals in the case of and we have seen that actually we don't have a closed form solution. Okay, so we have to rely on the tabulated data of phi. So that's why people have came up with a phi function so that like we can refer to phi and tables and so on. Okay, to come. So this may be some value, and then you look up at the table and so on. Okay, so so we leave it there. Okay, and to find the PDF, Okay, so to find the PDF, we know, right? To find PDF, we have to differentiate the CDF. Okay, so that's by now we know. Okay, so to find the PDF, we will do the, so PDF is denoted by small f, so d by dx of the capital F, and this is d by df, which is nothing but like this guy from here, and we have to take a derivative of this. So yeah, so here like derivative of this, so you will apply like a chain rule here, right? So this is like x is inside and it's in type of some function, right? So it's like phi of g of x form, right? So here like the scalar should come out, okay? Because you have to take derivative using the chain rule. You have to take the derivative, right? So this is like phi of g of x, okay? Where g of x is x minus nu by sigma. So the derivative of this guy is d phi by dg and dg by dx. So this is the chain rule. Okay, so this is how that fxx will be. Okay, so this is phi prime times. So and the derivative of g prime will be yeah. So this is like 1 by sigma will come out, right? So 1 by sigma will come out. So that's, so this is what will happen. So phi prime is phi prime of this, and then the g prime was just 1 over sigma. So this was our g prime x. 1 over sigma is there, right? So this is and we know that phi prime will be like and this is like z, right? So this is z because like x is sigma z plus nu. So we know that x minus mu by sigma is nothing but like I mean this is like we can see this as a PDF of z. Okay, so I can write this as a z, and I could have like written this whole thing as a z also, right? If it is confusing you, then I could have written this as fz z. Okay, so like while computing with explicit values, these things will be given to us. So this will be eventually some number. Okay, so this is the PDF expression of PDF for the normal. Okay, so now we have derived CDF for the normal, which can be left like this, and PDF of the normal can be left like this. Like, and then like we know this guy, so we can in the formula for the PDF of the standard normal. Okay, so PDF of the standard normal, you know, so you put it there. It's just that the variable has changed now. Okay, so it's just that the variable changed now. So you put those variables here, and then we are done. Okay. Okay, so so these are the CDF and PDF, and yeah. So if x is a normal random variable with mean mu and variance sigma square, that is this. So if fx is normal and it's denoted like this, then fxx is this, and so it's something that we just derived, and it's like we are summarizing things in one slide. And then fxx is this. The CDF is given by this, PDF is given by this. We have just derived this, and now we can also write the probability, right? So this is what we care about a lot, right? Because in reality, we are supposed to find probabilities, okay? Because we are solving problems, then we are dealing with probability calculation. So this is what we need. And this comes from here, right? So remember probability that A less than X less than equal to B is computed via CDF, right? So fxb, right, minus fxa, right? This is what how the probability is given using CDF, right? And this is what we have used here. So phi of b will be b minus this, and then phi of a will be in place of x you put a here, right? So this is how we will use these formulas to compute the probability. Okay, so we will see some examples on this shortly. Okay, so this is the solved example for the normal. Okay, so let x be normal. So this is the mu, the average value that this random variable takes, and then the spread or the variance is given by this 4. Okay, Okay, and physically you can make sense, like spread has to be something positive, right? And find the probability that x is less than 0. Okay, so what is the probability that x is less than 0? And find the probability that x is greater than -7 and less than -3. Find the probability that x is greater than 3 given that x is greater than -5. Okay, so this is the problem and we want to solve, and we know that it's a normal, not standard, because the mean n is not 0 and variance is not 1. Okay, so so how do we do the first one, right? So probability that x is less than 0, right? So probability that x is less than 0, this in terms of CDF, remember when computing the probabilities, we use generally we use CDF, right? So what does this mean, right? So probability that x less than 0, this is in terms of CDF. What is this? This is fx0, right? This is exactly means probability that x is less than 0, right? So we have to like substitute this in our formula. So this is the formula, right? Phi of x minus mu by sigma. Okay, so fxx is phi of x minus mu over sigma. Okay, so phi of x minus mu. So okay, so x is 0 minus and mu is -5. Okay, and sigma, remember this is like sigma square, right? So you have to take a square root of this to get sigma. Okay, remember that normal distributions are written like this, mu and sigma squared. So sigma will be square root of this. So divided by sigma, right? So which is 2 in this case. Okay, so and then this will be phi of so 5 by 2 is 2.5, and we will look into the tabular data. Okay, so get the value from table. Okay, so I will leave it here in the exam also. Like if you want, you can leave it up to 5 value. Okay, because after this is just it's looking up in a table, right? So you can leave it up to here, and okay, so and then we have this, right? So in this case, this will be, we will use the formula that we described right before. So this is like fxb minus fxa formula, right? Here b is like -3 and a is -7. So if we do this and fxx was phi of x minus mu by sigma, right? So this was the formula we recall. So fxb will be b minus that, right? So this is like -3 minus of -5 by 2 phi of that, and then minus of phi of -7 minus of -5 by 2. Okay, so this is like our b, and this is like our a. So these are like a and this is like b for us, and we put it in the formula and we can like leave it like this. Okay, like a further simplification could be it's like 1 here minus phi of -1. Okay, what is phi of -1? So do you recall what was phi of -x in terms of phi x? Right? What is the, do you recall this? Phi of -x in terms of x. Let me know in the chat. Phi of -x in terms of x. Okay, 1 minus phi x, Mehul, yeah, as always, very fast. So phi of x is, or in other words, to remember this is phi of x plus phi of -x is 1. Okay, so this is something you should always remember. People may not give you table for phi of -x. Okay, so but you have to remember that, translate this into positive. Okay, so this is like 2 times phi of 1 minus 1. Okay, so you can leave this up to here in exam. Okay, the tabulated data are there, and you can always stop here in assignments or exams or okay. Okay, now let us try to prove the third one. Okay, so we can do that. Okay, so this is like, let us say 1, 2, 3. Okay, so this is the third one. Now this is conditional, so we invoke the definition. Okay. probably that x is greater than -3, given that, oh, okay, not given that, but it's like intersection, right? So this is like comma, intersection and comma are the same thing, and x is greater than -5. So, and then divided by probability that x is greater than -5, right? Okay, so the intersection of x greater than -3 and x greater than -5 is x greater than what? Tell me, this is on the negative axis, right? So you should not get confused, right? So x greater than -3 and x greater than -5, the intersection is like, it's like -3, 0, -3, and -5. Okay, so x greater than -5 is like this guy, and x greater than -3 is this guy. Okay, so the intersection will be -3, right? So it's like probability that x greater than -3 divided by probability that x greater than -5. And from here onwards, like somewhat we have already figured out. So, so this is given in terms of greater, and phi is given in terms of like less, right? So we can take a complement. So this is like 1 minus probability that x is less than equal to -3. And this is like 1 minus probability that x is less than equal to -5. And now we know that these are like phi values, right? So this is like phi of -3, and this guy is like phi of -5. Okay. And after that, I leave it up to you. Okay, so because phi values are like known, so you will use this this form, and then yeah, and you get, finally you get something in terms of phi. Okay, so we can solve problems with normal distributions like this. Okay, using this phi values, and phi values we keep it, we don't go for explicit answer, we just leave it there. Okay. Okay, so this was the solved example, and okay, so here what I'm trying to claim now is that linear transformation of a normal random variable remains a normal random variable. Okay, so if I do a linear transformation of a given normal random variable, then the claim is that the remaining one will remain normal random variable, and to make it into a like a normal random variable, like we have to make sure that like it satisfies those like it satisfies those PDF and so on, right? Okay, so here this is the claim, right? If x is some normal with mu x is the mean, and sigma x is the variance, okay, and y is some linear transformation of the normal, which is in this case is the x is the normal, where a and b are scalar. Okay, so this is the linear transformation we are talking about. Then y remains normal. Okay, where mu y is a mu x plus b, and sigma squared is given by a squared and sigma square. Well, I think I don't have to spend too much on this. Like this should come up with, so to get this, you know what to do, right? So you just the expectation, and then linearity of the expectation, and then the expectation will look like this, and the variance will also look like this. Okay, so like this. Okay, this will be a square, sigma x square, and so on. So here it's very straightforward. Here I don't think there is much to do here. So why we are given is like ax plus b, and this is nothing but a sigma x z plus okay, yeah, okay, what I'm trying to do now is x, I have transformed this into standard normal. Okay, so so x I can write in terms of standard normal. This is what we have seen before. Okay, so where z is where z is standard normal, right? So it's like 0, 1. Okay, so that's like the, and then there will be b also. Okay, so this will be a sigma x z plus a mu x plus b. Okay, and now we can go ahead and compute expectations of y, and this will be like a sigma x expectation of z plus, and the expectation of this guy will remain the same guy because these are like constant, right? So expectation of a constant is the same constant, right? Average value of a constant is constant, right? So this okay. So here it will be like so this guy will be 0 actually, right? So and is this x? No, this is not x. This is we are talking here, right? So this is 0 because this is standard normal. 0 and this will be a mu x plus b. Okay, so this is the expectation that we have to prove, and then variance also you can compute, which is variance of a sigma x z plus a mu x plus b. Okay, it's like just in place of y I have put this, and then using the variance properties I have a square sigma square variance of z, and variance of these guys will be 0. Okay, because variance of a constant in 0, because variance of a there is no spread in constant, right? So constant data does not have any spread. Okay, so that will be 0. So this is like a square sigma square because the variance of this is 1. So these are the things that we needed, right? So yeah, so from here like we can write down that y is indeed a normal, and it can be seen as a normal with parameters a mu x plus b and a sigma x square. Okay, so what I will do next is something called gamma distribution, and gamma word that you know is also somewhat related to the gamma function that you may have seen before. So okay, I'm not sure if you have seen gamma function before, but what you may have seen is the factorial, I think. Okay, so factorial function is like we know, right? So this is like n times n minus 1 times so on, and then up to 1. Okay, so this is the factorial, but gamma function is a extension of the factorial function you can think of, because factorial is defined only for integer values. Okay, so this is like extension of factorial. Okay, so gamma function is a extension of the factorial. Okay, it's like, I believe it was given by Euler. Okay, so Euler. So, and we know that factorial holds for like integers only. Okay, like positive, integers, and the question was like, can we extend this factorial function to something that holds for like for general case, right? So for instance, here I have 0, 1, 2, 3, and so on, right? 4 and so on, right? So it's at 1, it's like 1, right? At 2, so 2 factorial is like 2 times 1. So it's like at 2 it's 2, okay? And at 3 it's like 6, right? So it's somewhere like here 6, okay? So you have these discrete values, like, but can you like can you like provide some kind of a interpolation or something like that of a continuous curve that defines values also for these intermediate real values? Okay, so can we do that? Okay, so that's when gamma function was discovered, and it gives you the so-called factorial values for like all the real values. Okay, so it's like all real, including rational, irrational, doesn't matter. Okay, everything. So that was like the analytical expression, or you can say that like what is that called, analytic continuation and so on, right? So this is like from discrete, I'm trying to make a continuous function out of that. Okay, so okay, now I will come back to this, how I will do. So it's a widely used distribution again. It's related to exponential and normal. So this is one of the things that I will prove why it's related to exponential. We have seen before, remember. Normal distribution also we have seen in the continuous case. So you have to recall this, and we will prove that in certain form, like in doing some limit or something, it approaches exponential and so on. Okay, so we will do this. But before doing that, as I just mentioned, I have to describe the gamma function, and gamma function is an extension of the factorial function for the real number. So if we restrict gamma function to the natural numbers, then this is how we will define the gamma function. Okay, this is like for n it will be n minus 1 factorial. So remember that, like, okay, so the way gamma function is like for n it's like n minus 1 factorial. Okay, this is just a little bit of thing here, like I did not write n factorial here. Okay, so for gamma of n is like n minus 1 factorial. Okay, so okay, so to get n plus 1 factorial, you should do gamma of n plus 1. Okay, so anyway, so in general, for any positive number alpha, okay, in general for any positive number alpha, so we are defining gamma for any positive number, okay, not for negative. Okay, so for any positive number, by number we mean real number. Okay, alpha, so it includes fraction and so on, right? So it's like, if I remember correctly, 1/2 factorial is like pi by 2, I think. Yeah, something like this. So there is a result like this. Okay, so the factorial of half is equal to pi by 2. Okay, something like that. So so in general, like we are extending our factorial definition to really general cases. So to do that, we need expression like this. Okay, so and this is like done by Euler, who proposed this extension of the. Please turn off your microphone. Okay, yeah. So this is the extension of the gamma function. Okay, so a natural question would be is like, what happens with when I substitute alpha to be some natural number, and then it should compute n minus 1 factorial, right? It looks a little bit not so trivial right now, but it should produce the factorial function for integer values of alpha. The curve, if we plot this, these gamma function values for different values of alpha, then this is what it will look like. Okay, so we know that at 1 it should produce 1, which is correct. Okay, at, oh my god, at 2, okay, what is going on here? Did my plot go wrong? Okay, I think by definition what we are doing here is like at 0, so gamma at 0 is defined to be 0 factorial is what? 1, right? So the way we define is like gamma of 1 will be actually 0 factorial, right? So 0 factorial will be 1. So that is set to be 1 here, and 2 will be 1 factorial, so which is still 1. Okay. But after that, it's like 3 factorial will be 3, gamma of 3 will be actually 2 factorial. According to the notation, it's always n minus 1, right? So 3 will come out to be somewhere 2 here. Okay. And then 4 will be like 6, I think. Okay. So somewhere there should be 6 here. Okay. So here somewhere it should be like 6. So at integer points, it should interpolate exactly those integer values, and then there is a nice continuation of this, and that will tell me for any arbitrary real value. Okay, so that's the extension of the gamma function that we are seeking in this case. So these are the properties of gamma function that we are not going to like do it today, because we have only like 4 minutes left. This is exactly the definition of the gamma function itself. This is not really the property, I would say, definition of gamma. Okay, but these are the properties of gamma function. Okay, and these properties will be very useful. Like from here, you can immediately see that gamma of n will be n minus 1 factorial can be proved for integer values. You immediately can see that can be retrieved from this property. Okay, because alpha plus 1 is alpha times, so it's a recursive thing. So, but this is holding for any real number. That's the okay. So it's like gamma of 4.5 is so I can break this down as a gamma of, so I can subtract like 1 from here. So gamma, so it's like 3.5 gamma of 3.5. Okay. So, and sometimes I can use this in the calculations. I can keep subtracting 1 and so on, and then make it very less. Okay. I mean, there is no guarantee that I will hit it 0 or something, but then I can go make this very less. Yeah. And yeah, so this is just a property of this, right? And then we can also prove this. The gamma of half is square root of a. So what I said is, I think I made a mistake initially. It's a half factorial is square root of pi. Okay, so this is the result we will prove here. Oh, okay, not okay, still half. Okay, so it's like gamma half is like gamma half is like half minus 1. Okay, it's like half minus 1. Okay, so this is like minus half factorial. Okay, so so minus half factorial is square root of pi, something like this. Okay? So we will prove these things in the next class. Okay, so we'll leave these things here and we'll continue in the next class. Okay, then have a nice day and bye.